So already you've probably noticed that the null distributions we've been simulating often exhibit a common familiar shape. And it turns out that this is useful because if we can predict the null distribution using theory, then we can find p-values in z-statistics without using simulation, which doesn't seem like such a big deal in 2020, but you can imagine not all that long ago when we didn't have this kind of computing power, and we certainly didn't have it in a phone in our pockets, that it was a big deal to be able to do this stuff without simulation. So we're going to make use of that common bell-shaped distribution by using the normal distribution to approximate what would happen if the simulation was done. And this works a lot of the time, but it's a good idea to sort of experiment to see when is this approach valid. So we're going to use the one proportion applet and play around with different sample sizes and different parameters and see when the normal approximation works well. So we're going to start by finding the ISI data in applets. If you haven't already bookmarked this page, I would go ahead and do it because we're going to use it seriously all the time this semester. And then we're going to find the one proportion app. That's the kind of data that we have here. Okay, so let's fill out the top row of the table together. So I'm going to change the parameter here to 0.7, and I'm going to change the sample size to 10. And I want to use a nice big number of samples. Let's just go ahead and use 10,000. That way we can get a really good idea of the shape. Okay, so looking at this null distribution, unfortunately it's a little bit skewed to the left. You can sort of see the tail there. The other problem for why the normal distribution is not a great fit here is that we really don't have a continuous smooth distribution across the scale, right? If your sample size is only 10, then you can't get any values in between. And so as far as the continuity goes, I would say there's pretty big gaps when we look at this one. So let's try changing the sample size. So instead of looking at a sample size of 10, let's look at a sample size of 30 here. That looks a lot better. I think there is still a little bit of a skew. I feel like there's a little bit longer tail there on the left side, but it's definitely close. So I would say here, maybe just very slight skew. And the continuity is better too, right? The gaps in between are smaller than they were before. So we've got less skew and also smaller gaps. And then the last column of the table is a sample size of 100, so let's try that. All right, now this is looking really good. I can't see that skew anymore. I would say at this point that the shape could be described as symmetric. And then also the continuity has gotten even better. Right here we have very small gaps. So now with a sample size of 100, I would say I definitely feel comfortable using the normal approximation here. Right? If I check this box, it looks like that's a pretty good fit for what's going on in the distribution. We can see across the board that as the sample size gets larger, the null distribution becomes more normal. First of all, the continuity gets better, the gaps get smaller as your sample size gets larger. Also, if you had problems with skew, they get better and better the larger your sample size. A larger sample size is required for normality when the parameter is further from the center, further from 0.05. So we saw that when the parameter was equal to 0.5, it was actually symmetric all the way from the beginning, no matter what the sample size was. With 0.7, it started off skewed, but it started to improve really quickly as we increased the sample size. With 0.1, it started off really skewed, and we needed a very large sample size to start to address that and make it more symmetric. So we're going to use validity conditions to help us decide when it's appropriate to use the normal approximation. In other words, when can we use the normal distribution instead of doing a simulation? And because the shape of the null distribution depends on both the sample size and the parameter, we need to take both of those things into account when we look at our validity conditions. So the guidelines that our book gives is that the normal approximation is going to be considered valid when the expected number of successes is at least 10 and the expected number of failures is at least 10. So if you think of how we calculate it, that takes into account both sample size and parameter. Because for the expected number of successes, you take the sample size and you multiply it by whatever the parameter value is in your null hypothesis. So we need the sample size times the parameter value to be at least 10. For the expected number of failures, we do the sample size and then 1 minus the parameter in the null hypothesis. So if that's the probability of success, 1 minus pi gives us the probability of failure. So this also needs to be at least 10. So if you think about how this plays out, if the value in your null hypothesis is 0.5, then that means that we only need a sample size of 20 to give us approximate normality, right? Because 20 times 0.5 is 10, so that's big enough. Whereas if the value in your null hypothesis is 0.1, we actually need a sample size of 100 to get to approximate normality. So we have to take both of these things into account. So what we've just informally proved using the applet is called the central limit theorem. So the central limit theorem says that if the sample size is large enough, then the distribution of sample proportions is going to have certain features. So a couple things here. When we say large enough, that's where the validity conditions come in, right? The validity conditions are basically letting us know, is the sample size large enough in this case to get away with using the normal approximation? Also, when they talk about the distribution of sample proportions, in practice for us, we're really talking about the null distribution, right? Because we're hoping to use this in hypothesis testing. So what we really want to model is the values that would occur if the null were true. Okay, so it says that if the sample size is large enough, the distribution of sample proportions will first of all be approximately normal. So that allows us to do the normal approximation. It also says that it will be centered at the long run proportion pi. So again, in our case, we're talking about null hypothesis testing. So we're going to be assuming that the null is true. So the distribution that we are thinking about, it's centered at the value from the null hypothesis. And we've just been using pi with a little zero, pi naught, to represent the value from the null hypothesis. We also have a formula for the spread of that distribution. So earlier when we looked at the standard error, we were just getting that from the simulation, but the central limit theorem actually gives us a formula for it. So here when it says standard deviation, we know that this is really a standard error because, again, it's the standard deviation of the distribution of sample proportions, right? It's the standard deviation of a statistic, and we call that a standard error. So this gives us a formula for the standard error. Also, you can see this confirms what we talked about earlier, that as the sample size gets larger, the standard error gets smaller, right? Because the sample size is in the denominator of that fraction. So as the sample size goes up, standard error goes down. So the validity conditions let us know when it's okay to do a normal approximation, and that allows us to use theory to calculate p-values in standardized statistics instead of using a simulation.